Alright, recording has started. We'll start the class. So welcome to our last week of Calculus 1. And we have an exam today. And we're going to run until from 5:30 to 6:30. And then at 6:30 you can start the exam. And I'll have it open. And you have to have it completed and back uploaded by 9 p.m. 6, 7, yeah, 2.5 hours window. Or maybe it's 8:30, one of those two. We'll check. And am I coming through clear? And let's do a practice quiz. Can I just get a verification that I'm coming through?
I can hear you fine.
Great. All right. Find all critical points and inflection points of the general formula for a parabola, ax squared plus bx plus c. And let me give you a minute on that. Okay, 20 seconds more. All right, so we take the derivative. We get 2ax plus b. And when we set that, well, let's take the second derivative as well. Let's do that over here. So when we set the first derivative equal to 0, we then solve for x. So negative b is 2ax, or x is negative b over 2a. And this is the standard form for the vertex of a parabola, negative b over 2a. And if you'll recall, we went over this once before, the quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. If you broke it up into the two parts, break it up into this fraction, and then plus and minus the same amount, you see that this is where the parabola has to have its either high point or low point. And then if we were like, because of symmetry, if we were a downward parabola hitting the x-axis, those would be the two x-intercepts, like this. And what this is telling us is f prime prime is always either positive or negative, because a is a constant. And if the coefficient a is positive, then we have it concave up. And if a is negative, you're always going to get a negative second derivative, and then it's always concave down. But the concavity is constant the whole time. It doesn't change as you move. And alright, so this one kind of sheds some light, uses calculus to kind of shed some light on some basic features of parabolas, and it's consistent with what we already knew. And number 2, f part A, f of 4 is equal to 7, and f prime of 4 is equal to 3, then approximate f of 4.002. Now you're going to need to draw a picture to be able to approximate that. You're going to have to put this and this somehow and give it meaning on your diagram, and that'll lead you to a reasonable approximation for this. Let me give you a minute for that. And Jay, do you see my camera image? I see it flashing, only while it's on the camera. Do you have any idea what that means?
I have no idea. I didn't get an image until about the second problem, so
Okay.
I'm not sure.
Okay. So my computer died this weekend, and it had given me some warnings. My computer and I have a special relationship. I know how to press its buttons, and it knows how to press mine. And it had, every now and then when I would turn it on, it would tell me hard drive not found and not be able to turn on. And so I had gotten permission to go into my office and bring my desktop from my office home, because with my vision difficulties I can't use a laptop. And so anyway, I had to switch on over to my office computer, because my home computer decided to stay with hard drive not found. Alright, so on this one, let's look at the visual interpretation of this. F of 4 is 7. We know that the function has to pass through this point. But does it pass through it like this? Does it pass through it like this? How do I know how it passes through this point? this tells me out. The instantaneous slope, as it passes through this point, must be positive 3. It's going upward, so that by the time it goes to the right one, it would go up 3 as it passes through this point. So it's coming through this at a fairly steep positive angle. Now, if we stayed on the tangent line, we'll go 1 to the right, go up 3. So if it had been going, like if I had to put a negative number here, then my approximating at a little to the right of 4 would have been a little less than 7. Because of this being positive, then a little bit to the right of 4, it should be a little bit higher than 7. Now, if this was 1, then every time it goes over 0.002, it would also go up 0.002. But since it's 3, the amount that it goes to the right, it's going to go up 3 times that amount. So my reasonable estimate for its new height would be 7 plus 0.006, because tripling that because of this, 7.006. Now, if you're able to get something in that ballpark, or something a little bit bigger than 4, bigger than 7, give me some feedback on that. Typically, most students can't the first time they see this in calculus. It's skipping lots for you. That's working fine. So a lot of people having some difficulties with my new computer. Some are good, some are bad. When I'm on my camera, I see a flash at times. Okay. And right. Wow, so something is off with my computer. And I started recording. Okay. Alright, so sorry that it's not a consistent image and transmission for everybody. I didn't get any positive feedback that people had gotten this. This is a pretty tricky problem. So I prepared another one. I wanted you to see if you can get the second one now that you kind of see what's being asked of you. So this is part B. If f3 is equal to 5 and f prime of 3 is equal to -2, approximate f of 3.01. So, draw a picture that makes that meaningful, and that allows you to get an estimate. about 30 seconds more, and we'll go over this. Alright, so this one, 1, 2, 3, I'm at a height of 5. I know my function goes through this. How does the function go through this point? We know it goes through in such a way that its instantaneous slope is -2. So if it went right to the right one, it would go down 2. So it's coming like this. And so now if I go to the right, now if it was -1, then if it went to the right 0.01, it would go down 0.01. But since it's -2, since it goes to the right 0.01, it's going to go down 0.02. So I would get about 2.98 right here. And give me some feedback on the correctness of that one. If you got that totally correct, give me a 1, 0 if you were kind of lost, and any number in between. Oh, thank you. It's not 3 point. Sorry. I made the mistake. Let me get feedback again after I do it right. It wasn't a little bit smaller than 3. It's a little bit smaller than 5. So, of course, you don't know if you got it right when I had the wrong thing. So the right answer is a little bit smaller than 5, like 4.98. Now give me feedback again on the correct answer. If you got that right or not. Okay. Alright, so this is one of the uses that we put calculus to, is to predict the future. We have data that gets up to the present. And then we look at, alright, what was our trends up until this point? And then how far can I predict into the future? Usually, our predictions in the future are only valid for very short distances. But for short distances into the future, you're much better off looking at what's been happening recently than just, projecting that it's going to stay 5. If it had been declining right up until this point, it's probably got some momentum built up. And we're going to look into today in another one of the primary uses of calculus. And but before I get into that, are there any questions? I'll come back to the main screen. Anybody have any questions we want to resolve before we go on? Okay, question about the final. Go ahead, Jack. Yes, I have posted both, a PDF and a Word document. And it'll become active at 6:30. How long will you have to take the final? Well, I hadn't totally thought about that. You're supposed to have 2 hours for the final. I'll give you 2.5 hours. I've been giving you 2.5 hours for each test, but I'll do that for the final as well. You're welcome. Any other questions? All right. So let me. Oh, I think Yoon has something. I'll wait for Yoon. And then I'm going to go and take you through let me do that real quick while she's typing. If you go to our discussions, where we had done other ideas before, here is discussions groups for the different topics, and final exam discussion forum. So nothing's been posted on any of these yet. I have very little experience with this. Maybe there's a better way that I should be setting these up, but this is just what seemed reasonable to me. Anybody has any suggestions, let me know. But like as you're running into issues with final exam review, this might be a place to put your questions, and then also be checking and answering other people's questions as well. And all right, let's start. Let me check over here. What time is the deadline for tests tonight? Okay, yeah, let me check that. See what I put. So if we go into modules, exam 4, and it says it goes 6:30 until 8:30. So 2 hours, 2-hour window for the exam, and we'll stop a little before 6:30. And actually, this is just how long this exam is up here. It doesn't prevent you from posting your exam. Maybe it does. Maybe you can't upload it after that. I'm not sure. All right. And let's go to 4.5, optimization problems. We're also going to do this section on Wednesday. So today is kind of just the intro to this. And it's a really valuable section. It's one of the big uses of calculus. What do we mean by optimizing something? Well, if you were to send a rocket ship to Mars, and there's been rumors for a long time that perhaps we'll be sending at some point a manned rocket ship to Mars. One of the things about building the rocket ship is you want to, you have very, very expensive materials. So you want to maximize the volume of the space inside the rocket ship. And so whenever you're maximizing or minimizing something, that's called an optimization problem. And at the same time, you would have special places like right at the front part of the cone of the rocket ship, where it might take a beating, hitting any objects, even in the atmosphere or out of the atmosphere. And so that material would be incredibly expensive. And then there you'd want to be minimizing the surface area. And probably on the whole spaceship, you want to be, we often have these dual goals. We're trying to maximize volume while we're minimizing surface area. We're going to take simpler problems than that, but problems where we might look at it and at first think, there's no way we can do this kind of problem, but we find that we can with the aid of calculus. So we're going to start with a problem. A farmer with 750 feet of fencing, wants to enclose a rectangular area and then subdivide it into 4 pens with fencing parallel to one of the sides. What is the largest possible area of the 4 pens? And, all right, I'm going to draw some possibilities for how the pens could look. And I'm going to ask you to use your intuition to, not any fancy math or not any math at all, just your intuition to answer some basic questions about this. And to do that, I'm going to have you go, if you go into Discord, you will see that I have made these groups. Jay helped me set these things up. Group 1 through group 5. And when you click on one of these, you'll be in that group as a text channel, and then you could always click back over here to this general text channel to get back to our general text channel, but you can go back and forth between discussing with your group and then back to seeing what's going on in the general text channel. And so I'm going to just we're going to go with the listing on the left in groups of 4. Adelaine, Alondra, Christian, and Ethan, you're going to be group 1. Herman, James, Jay, Karina, you're in group 2. Kendall, Megan, Michaela, Nehemiah, you're in group 3. Rue, Selena, Scott, that's Stephen Allen. Rue, Stephen Allen, Scott, and Selena, you're in group 4. And Sierra, Sophia, you're in group 5. Actually, Scott, all right. But anyway, that'll be fun. You all get into those groups to discuss briefly your answers, what you think are going to be the answers, and then I'll ask you for feedback from each of your groups. And let me go back to this question that Addie typed. On the final, just on the chapters on the review, like not including the chapters tonight test or what we're learning for the next few weeks. All right, the final covers everything that we've done in this course. And so what I put on in the final exam review goes up to the material that you have been studying for exam 4. So I did not put problems from, I think it's chapters 4 and 5 on the final exam review problems. thinking that, you've just studied for this exam 4, so that should be pretty fresh for you. The stuff, this is our very last section on optimization. Yes, you could have something on optimization on the final exam. All right, so let's go to here, and here's the question. If they just said, give me a shape that has the optimal area and it's rectangular, then the answer would be clearly that it would be a square. There's the maximum area that you can get. If you make a long skinny rectangle, you're not going to get as much area. You get the maximum area from a square for your 750 feet of fence. Now, when we subdivide into 4 pens with fencing parallel to one of the sides, it means, I'll show you 2 possible ways to do it. One possible way is that the outer portion is still going to be a square. And then I'm going to put 3 more partitions. And that is going to somehow look like this. And that would be my way to get possibly the optimal area where the outside edge is still a square. Now, another possibility is that you start out with something like this, and then you chop it up so that after we've made 3 separate internal fences, all parallel to one side, as it's saying, that now we have here the outer edges, here and here is a square, here this and only this is a square. So, case is, does your intuition tell you that the way to subdivide this so that we get the optimal area, most area, is case 1, case 2, or case 3, where there's going to be no squares involved? The way that we eventually divide it up is that you're not going to have the outer edge be a square, nor any of the inner portions be squares. They'll be just something non-square at all. And take a moment, get into the correct group in Discord, and see what consensus you might come up to. If you have a majority rule or something, you could at least put that. And then after a little bit, I'll ask for your feedback. Which of these cases, 1, 2, or 3, do you think is going to be the case? Okay, in about 20 seconds, I'm going to ask you to have one member of each group go to the main text channel and report on what your group is thinking. Consensus this, or kind of split between this and this, and just give us a little description on.
Could you tell us
Yes. Okay, if you could give me some feedback on the main Discord chat panel on where your discussion went. All right, we're seeing more going for case 2. Some folks still can't see the whiteboard, dog. All right, I'll have to look into some kind of issue with my camera in this computer. All right, so the biggest, though, consensus was for case 2. And let's work out the problem now. We're going to kind of slowly get at the problem, though, instead of jumping right into the answer. Because I want you to understand the complexity of the issues rather than just see a fast calculus shortcut to an answer. Let's draw a picture of the situation that isn't favoring either one. That's just kind of not necessarily squares, nor the outer thing a square. And let's label some things. If we call this side x, and then all these would be x, and then the region y could be, as long as you're clear, you could make y be all the whole distance from here to here, or y be just the distance here to here. Either way, it doesn't matter. And I'll make it, all right, let's do it, y from here to here. So then if I have x and y, and I'm going to also put 4y, because the area, according to this picture, is going to be x times the whole distance across, which is 4y. Area, which is x times 4y. And suppose I had some possibilities for 750 feet. I just listed a few. Like if I did 70, 80, 90 feet. If x was 70, then you'd have to take a little equation. Now we know that it must be true that, how many x's are there? 1, 2, 3, 4, 5. 5x plus, now the y's, 1, 2, 3, 4, 5, 6, 7, 8, plus 8y has got to use up all 750 feet of fence. So when I pick a number like 70, I can just plug it in here. And if x was 70, 5 times 70, which would be 350, subtract the 350 from both sides, 8y would have to be 400, and then y would have to be 50. And then the whole width would be 4 times that, which would be 200. And the area would be 70 times the 200, 14, and then 3 zeros. And I would get 14,000 area. And And when I do it with 80, and I solve again, my 4y would turn out to be 175. The y would be whatever that is divided by 4. And it turns out that this would once again be 14,000. And then if my x was 90, plugged in 90 and then solve this thing for y, my 4y would turn out to be 150. And this would turn out to be 13,500. Now these are all square feet. So if I just had this much information, my tendency would be to think, I'm going to find the optimal area. Maybe, certainly I'm better off with x being 80 than x being 90. And these two coming out with the same equal values could be, maybe it's decreasing on both sides of this. But that would be kind of assuming that I would get some kind of parabolic shape, that I would get, some kind of highest point, maybe halfway in between 75 and 80. And that would be my optimal kind of thing. But just by plugging in some values, we can kind of start to get a feel for the area of fencing that we can get with this. So whenever there's an application problem, this was one of the reasons I was really, really strong at application problems, was because I never jumped into the math of the problem, not for a long time. I would play around with numbers, and I would just say, well, what if this was this and this was this, and then, just get a feel for, maybe I could understand the problem this way. And, all right, so this gives us a little more information. Now let's get into optimization theory. How do you optimize with calculus? So, in general, an optimization problem is one that you're going to maximize or minimize something. So your first step, a reasonable first step, is to put your goal. And in this case, what's my goal? Am I maximizing or minimizing something? Well, he wants the largest possible area. I'm maximizing area. Okay. Next, in an optimization problem, I want to look at what is given. There is some basic information that will be given. And the basic information was the layout of the fence and the 750 feet. But we get all of that incorporated with a quick diagram and with this equation. 2, 3, 4, 5 of those x's plus 8 of those y's, has got to be 750 feet. And again, we also have the diagram to help us out. These two pieces of information are given. And then we go to number 3. We write an equation for the thing that we're trying to optimize. So we're going to maximize what? A for area. But we need an equation for A. And according to this picture, the A is, well, it's a rectangle. It's the width times the length. And so it's x times 4y, or 4xy. So we write down what we're trying to do. We're trying to maximize this. Now, in this equation, A equals 4xy, we are not able to handle this kind of complexity at this point in calculus. This is a more difficult equation than any that we have come up with so far. Why is this problem more difficult than any that we've done so far? It looks kind of simple. Area is 4 times x times y. It has one output variable and two input variables. We have never dealt with two input variables. So this is kind of like, x is the input, but also y is the input, and then a is the output. And now we are going to eventually be able to handle functions of more than one variable, because the real world that we live in is a three-dimensional world. And we're going to have to do kind of problems in 3 space, and we're going to have x, y, and z axis, and we're going to have like the temperature in a room as depending on your position in the room, because you have a fire in the corner of a cold room. And so your x, y, and z coordinates of where you are in the room is going to determine what the temperature is at any point in the room. And then so then we're gonna in calculus 3, you'll learn how to have more than one input variable and one output variable. But where we are right now in calculus 1, we can only handle one input variable. So we need to take this equation. So the problem two input variables, one output variable. We got to get it down to one input variable, one output variable. That's something that we can then maximize or minimize with calculus. How do we do that? We take this equation and we solve it for either x or y, substitute its value into this equation, and we turn this into one variable problem. So let me erase this stuff up here and do that. So let's say I want to get rid of the y. I'm going to take 8y equals 750 minus 5x. So then y is equal to 750 over 8 minus 5/8x. Then I'm going to take the area equation. Area equals 4x, and then replace y with 750 over 8 minus 5/8x. Now let's multiply that out. 750 times, well, the 4 and the 8 are going to reduce. And so that's going to be a 2 on the bottom. And then the 2 goes into 750, 375x. And then the 4 and the 8 reduce, 5 halves x squared. Alright, now this is if I visualize this, and now just, this is the area as a function of just, remember the picture, the x's were these verticals, and the y's were this. So area strictly is a function of my choice for x. And when I do that, I can think of it as x and a. And what shape is this curve? You might be uncomfortable just because that's an a, but think of it as a y for a moment. Just replace that with a y. And then, oh yeah, this is a parabola. It is a downward parabola. And downward, with the leading coefficient for x squared, when it's negative, it's going to be like this. And then we are going to be finding this point right here, the vertex of the parabola. So we can do that with calculus. Once we have our optimization equation written in terms of one input variable, we then can go dA dx is 375 minus, and then multiply this, 5x. And then, now we could actually do this without calculus as well, because we know this is a parabola. We could find the vertex of a parabola with the vertex formula. But calculus will quickly zip us right to this. We bring the 5 over, divide by 5, x is equal, and then 375 divided by 5 is 75. And remember when I made that chart a little earlier, 70 and 80 had given us the same areas, and halfway in between was 75. So if this was 75, then we could go back to the equation. 5x plus 8y is 750. Plug in the 75 in here, and then we can figure out what the y is. And we can get a value. And then we can use the x and the y then to multiply out and get the area, the largest possible total area of these pens. And we're running out of time here. It turns out that the largest possible area happens when x is 75, and it's not going to be a square for the total outer region, nor are the internal regions going to be squares either. So it was choice 3 of those 3 choices. None of the squares did it. And we will do more of this type of problem on Wednesday to get you ready for the optimization homework problems. And that's where we'll stop now. So I'm going to adjust the deadline to 9 p.m. instead of 8:30, because like you have kids and so on, you might have some interruptions and so on. So I'll do that. And okay. Sorry about the bad connection tonight. I did have a class earlier today, and everything seemed to go fine there, so I'm not sure what went worse now. All right, so the exam will be ready to go in just a couple minutes. Any questions? You're welcome. And I'll see you all on Wednesday. What homework do you have left to turn in? So there's going to be an assignment on the 4.5. There was 5.5 was due today, substitution rule. 4.5 homework, I'm going to have that due at the final exam, just before you do the final exam, which will be on Monday, May 11th. And then there is the review for the final exam, and I'm not going to take any points off if you don't do that, but I consider it essential, but I'm giving bonus points for doing it. You're going to get 100 points. If you do at least half the problems, you get your lowest homework grade replaced with a 100. And if you do at least 90% of those review problems, you get your two lowest homework grades replaced with a 100. And those review problems, I really emphasized the basics. Okay, I hope the video is fine too. I'll post that video very soon. All right, we'll stop here if there's no more questions.